Hi guys, today we'll be presenting our final project on multi-agent drone control with reinforcement learning. This is an overview of what we will be covering in this presentation. So to introduce the topic, multi-agent drone systems are increasingly used in real missions such as NASA's Starlink formation flying system, which demonstrate autonomous coordination in space. While single drone control is largely solved, coordinating multiple learning agents remains a major challenge. Reinforcement learning is attractive because it can learn control policies directly from interaction, but most existing solutions rely on black box frameworks. In this project, we will build custom multi-agent PPO algorithms from scratch in PyTorch to study coordination in realistic drone physics. Our focus is in understanding how learning dynamics change as coordination requirements increase. The main motivation for pursuing this is that the core difficulty in multi-agent learning is non-stationarity. From any single drone's perspective, the environment keeps changing because other drones are learning at the same time. This breaks the assumptions of standard reinforcement learning and often causes unstable or divergent training. Independent learning works for simple tasks but fails as coordination requirements increase. Our key question here is, when does decentralized learning break down, and how much shared information is needed during training to recover stability? The problem statement over here is defined as being the goal is to train n number of drones to coordinate without a centralized controller at execution time. Each drone observes only local state information and outputs continuous mode RPM commands. Despite decentralized execution, the drone must collectively achieve global objectives like stable hover, formation flying, and leader follow navigation. The challenge here is that coordination must emerge through learning, not through explicit communication or centralized control. This makes the problem high dimensional, non stationary, and tightly coupled across agents. Some related work covering this is that fully centralized control does not scale and creates a single point of failure. Independent PPO treats other agents as part of the environment but suffers from severe non stationarity in coordinated tasks. MAPPO addresses this using centralized training with decentralized execution, where agents act independently but learn using a shared global critic. Prior work shows MAPPO works well in domains like StarCraft, but less is known about its behavior in realistic drone dynamics. Our work extends this by implementing MAPPO from scratch and evaluating it on physically grounded multi drone coordination tasks.
All right, let's talk about the approach. The core architecture is MAPPO, which follows a centralized critic and decentralized actors paradigm. The centralized critic is only used during training to solve the global credit assignment problem. During execution, only the actors are kept and they operate independently. Initially, the actor network is an MLP with shared parameters, which forces the agent to learn a common policy. And to evaluate our implementation, we designed experiments with three levels of increasing complexity. Level one was multi-hover for baseline flight. Level two was multi-spiral for tight coordination. Level three was heterogeneous flocking, which consists of leaders and followers. All right, let's talk results. In multi-hover, we see the first clear divergence where the IPPO's performance is inconsistent, and this is because it has independent agents which treat neighbors as stochastic noise, which causes the value loss to spike and the entropy increases and then plateaus as seen over here. Even regular PPO with a single centralized controller would be more predictable as it would treat the whole swarm as a single agent, but then it would also suffer with scalability. But MAPPO solves this with high sample efficiency. As we can see the early training logs over here, we can clearly see the value loss already settling and the entropy decreasing, and it also obtains consistent returns. So the return variance reduces to zero and also maintains maximum episode length. Evaluating this with qualitatively with simulation, we can see the clear difference. On the left here, we can see the IPPO agents which are jittering a bit, and the MAPO agents are moving fluidly. And in the multi-spiral task, we can see the evolution of coordination. At 1 million steps, the agents are merely learning to fly. At 3 million, the geometry is there, but it lacks precision. And at 5 million, the policy converges fully and we achieve close tracking as seen here. And this also matches with the return curves from the training logs over here.
One of the biggest challenges we faced was reward shaping. Initially, quadratic penalties cause agents to aggressively terminate themselves to avoid future penalties, so we switched to smoother exponential rewards. We also saw value loss explode to extremely large values, which completely killed exploration. This was fixed using value clipping, reward normalization, and higher entropy. Finally, training performance was a bottleneck. Running many parallel environments slowed us down significantly. We optimized collision checks and normalization using vectorized NumPy and torch operations, which improved training speed by more than 10 times. Going forward, the main scaling bottleneck is the centralized critic. Our next step is to distill centralized value estimates into more compact representations such as invariant embeddings or latent task abstractions instead of raw global states. On the simulation side, we want to validate these policies on real drones to study sim-to-real gaps. Finally, we plan to quantify non-stationarity directly by measuring policy drift, gradient variance, and value stability during training. The key takeaway from this work is that centralized training becomes essential once independent learning starts to diverge. We found that the hardest problem in multi agent drone control is not physical control but managing the information bottleneck during training. Since the centralized critic scales linearly with the number of agents, this points towards attention based and permutation invariant architectures as the next step for scalable drone swarms.